All right, back with video 10B. We're going to look at some more exponential functions. So we've got an example. If we look at a mold colony was cultured by a scientist in a petri dish for 1.5 days, the scientist would like to use hours elapsed to predict the mold count in millions. So over time, this mold would probably increase. So the data, the scatter plot, and the exponential equation are given in your notes. So here are the data. We see how many hours have elapsed. And then we see the mold count. Again, that was in millions. And so we're going to see if we can use the number of hours to help explain the amount of mold in that petri dish. So you have your scatter plot. If you look at that scatter plot, I hope that it's very clear that this is not a linear model. There's definitely not a straight line to this. There's clearly a curve. So since there's a curve, exponential is one kind of equation that has a curve to it. Why might an exponential growth model be appropriate here? Not only is there a curve, look what happens to the mold count. As a small amount of time goes by here, as the first few hours go by, the mold count's increasing, and you can probably see it better that the numbers are increasing as time goes by here. But once we get over past 12 hours to 15 hours, 18 hours, and look what happens between 24 and 36 hours, the mold count really starts to increase at an increasing rate. So the mold count is increasing, it's also increasing at an increasing rate, so that's why an exponential growth model would be appropriate. Okay, so we're going to use an exponential model for this data. So you have the exponential model in your notes. It's given right below the scatter plot. So here it is. We could add a hat to this that we're using hours to help predict the mold count. So here's the equation. It's in that form of an exponential equation. Remember, we had y equals a times b raised to the x power. This is the base b of that exponent x. If you look at that base b, it is a number bigger than 1. Since it's a number bigger than 1, that happens when we have exponential growth. If it's a number between 0 and 1, or squeeze between 0 and 1, then we would have exponential decay. And so we'd like to use this equation to predict the mold count at 30 hours. 30 hours is within the range of data that we have, so we're allowed to do that. That won't be extrapolation. And 30 hours is x, so all we have to do is plug in a 30 for our x variable here. So we would predict the mold count to be and that's just an operation you would type in your calculator. You have a caret key raised to the 30th power. And if you type that in, mold count again was in millions, we would get 49.39 million. And we could have done that for any value, really, any number of hours between 0 and, say, 36-ish. All right, part C. Explain why we would have reservations about predicting much beyond 36 or so hours. We'll go back and look at the graph. If you look here, here's 36 hours. We would guess that this would probably continue for a while. However, it is a little petri dish, so how much mold can actually squeeze into that petri dish? There might be some sort of cap here. If you're taking biology class, you might know about like logistic models where things kind of increase but then they level off. Population of fish in a pond, you can only fit so many in there. You can only fit so many mold in a petri dish. So beyond 36 hours, at some point, I don't think that can grow forever. There might be some sort of cap. So Predicting beyond that would be extrapolation, and the model could clearly change. So a couple things. It's extrapolation. And the second thing, if we go out too far, there's probably some sort of cap. So eventually there's some constraints maybe due to the size of the Petri dish. It might be okay to predict what happens after 37 hours, but you know, we probably don't want to go out and find out what happens after 50 hours. All right, so this one was exponential. We looked at the equation. You could recognize that as an exponential equation. We know when it's okay to do some predictions, when it's not. Let's look at a second one. Second one, some percentage of the population are diabetic, in which the body is unable to produce insulin. So insulin's needed to process glucose. To provide the hormone, an injection of medicine containing insulin is taken. As time elapses, that insulin breaks down in your body. So the variables that we're going to look at are time since entering the bloodstream in minutes and the units of insulin in the bloodstream. So a doctor took measurements on one patient in a controlled environment, and we have some data. So this is the amount of minutes that have passed, and this is the units of insulin. And the first thing we're going to do is look at the scatter plot and then explain in words why an exponential decay model is appropriate. So if you look at the scatter plot, we've got time since entering the bloodstream in minutes here, units of insulin here, and if we look at the amount of insulin in your body, when you first get the injection, you have a lot of insulin, and then as time goes by, that insulin starts to wear off, so it's decreasing. Not only is it decreasing, it's decreasing at a decreasing rate. You'll see that it's rapidly decreasing to start, and then once we reach like 20, 30 minutes, it's decreasing, but at a decreasing rate. So actually my answer goes back here. Why an exponential decay model is appropriate. Insulin is decreasing. Our scatter plot definitely did not look linear. Decreasing. And not only is it decreasing, it's decreasing at a decreasing rate. So we're going to use an exponential decay model this time. You've got actually two of them given here. We have to figure out which one of these is the correct one. So remember, this is a decay model. In general, exponential functions look like this. Our base B, is it 1.95 or is it 0.95? Which one? The big thing here is it's decay, right? So since it's decay, you only have decay when that value, when your base value is a number between 0 and 1. Can't be 1. Can't be 0. But it's squeezed in there between 0 and 1. If the value of B is a number bigger than 1, that's the last example where we had growth. So for this one, since it's a decay example, it's got to be this second one. And so this base B, when it's between 0 and 1, that's when we have decay, which clearly we have here. This would be an example of an exponential growth equation, and that certainly is not appropriate. You know, you get your shot of insulin, the level of insulin goes up and up and up over time. That doesn't make any sense. It's going to decrease over time. So second one. All right, next thing, let's pick the correct equation, the second one here, and we're going to do some prediction. Use the correct equation to predict your insulin at 1 hour. Now, a little confession, we're definitely doing a little extrapolation here, right? Our data only went out to 45 minutes. But as you can imagine, over time, what's going to happen with the insulin level, it's just going to continue to decrease, right? This is probably going to get closer and closer and closer to zero. And we're not extrapolating a whole lot here. The pattern's not going to all of a sudden change and go back up. So it's pretty safe in this one to do a little bit of extrapolation. So we're going to use, this was our correct equation. What happens after 1 hour? X was time, but it was time in minutes. So we'll plug in 60 minutes for X and see what happens with those units of insulin. Again, this is a type in your calculator, 10.405 times 0.95 raised to, use your caret key, the 60th power. And we find out that the model predicts 0.479 units of insulin. All right, those are some examples with exponential equations, both an example of growth and an example of decay. Again, whether it's growth or decay really depends on that base. If the base is bigger than 1, you're going to have some growth. If the base is a number between 0 and 1, we're going to have decay. You should be able to recognize from a scatter plot, hey, that doesn't look linear. This is the kind of model I should use, and you should be able to know how to make some predictions when it's appropriate and when you should not. So that's it for exponential.